So this I2c is one master, one slave. So one slave means slave address fixed. Okay. So first state it is as well as your start state. Okay. So in the start state, what will happen? Master should send the start signal. So in my code, like in this project, master is your test bench. You are designing the slave. Okay. So master should send the start signal. So start signal means SDA should go from high to low when your SCL is high. So before this, I can have one idle state. So in this time, your SDA should be 1. Okay. So that when master will make this SDA 1 to 0, then slave will detect it as a start state. So after start, then it is register address state. So here, master will send register address 6-bit, so 7-bit plus write read signal 1-bit, so total 8-bit. Okay, serially.
Okay.
So this I will be providing from the test bench. So slave will take this data and convert it to parallel. It should take 8 clock cycles. Next is address acknowledgement state. So here slaves should send acknowledgement signal. Acknowledge signal means it is like in the 9th clock cycle, your STA should be equal to 0. 0 means acknowledgement, 1 means NAC. So if, so in this case, if STA equal to 1, that means slave sends NAC signal, then what will happen? Master should drop the transaction. That means master should simply go to idle state. Okay. Because the slave is not responding. So next will be your after register address, depending, it may be write state or it may be read state. So here data write state. So here the if write read signal equal to 1, so 1 means it will be read, 0 means write. Okay. So 0 means it is the write operation. So master will send 8-bit write data. Serially. So slave will take this data and convert it to parallel. Okay. So whatever is happening here, same thing is happening here. Okay. Whenever master is sending data, master will send serially, slave will convert it serial to parallel. So in the 9th clock cycle, it is write acknowledgement. So it should be from slave to master. Okay. So now for the read operation. So read operation, it is opposite. Slave will send the data. So read operation. So here slave will send data.
Parallelly.
No, serial. SDL line, it is 1
Okay.
bit.
Okay, ma'am. Okay.
Okay. So see,
Okay.
this address, according to this address, data is sent, data is stored parallelly. In the slave, data is stored parallelly. But whenever it will send, it will convert parallel to serial, then it should send, because SDL line, it is just 1 bit.
Okay, ma'am. Okay. And my master will convert it into parallel again.
Yeah. Because whenever we are storing, we store it normally parallel format, because I am sending one 8-bit data. So it should be stored in 8-bit format, but whenever I am transmitting it, it can be serial or it can be parallel. So what is the advantage of serial? My number of, see, whether it is 64-bit data, whether it is a 128-bit data, always there is only one signal or one line present. That means area wise it is less, it is taking less area. But again, what is the disadvantage? It will take more time, because to send 8 data, I have to wait 8 clock was. In the parallel, what happened? At a time, I will send 8 data. So if number of data bits increase, in parallel, size will increase. But what is the advantage? Time will reduce. So if I don't have any size constant, like let you are doing something with your laptop can have more size, so I can take to parallel transformation. It just depends on our requirement. Okay, if I don't have any issue with size, I can go with parallel transmission. If I am concerned about my size, then I should go to serial transformation or serial communication. Okay.
Okay.
So here, master should send the acknowledgement signal if ST is equal to 1. That means master sends next. So master should drop the transaction. Remember, whether it should start the transaction, whether it should stop the transaction, all this decision depends on master, not in slave. Okay. So here what happens? Okay, for the simplicity, if some error happens, we should drop the transaction. But what you can modify, let in the address there is some error. So instead of going to idle state, you can go to again register address state. It is like repeated start. That means I'm not dropping the transaction. I'm just trying to restart it. So it's up to you. You can go to idle state or you can go to here. Now next is it depends on how many transactions are there. So here after one transaction, I should stop the transaction. Let you want know I want to transfer a 64-bit write address. So 64 write data. So 64-bit write data means 888. It will take 8 times. So you have to loop this part 8 times. So it is project specific. So at the start of your project, you should fix what is your address size, what is your data size. So depending on your address size or data size, you should write this code. So here I have taken address 8, data 8. If you are taking 64, then these two things, it repeated for 8 times. Remember in SD, after each 8 clock cycle, slave or master should send the acknowledgement and lag signal. You cannot directly send 64-bit. 8 clock cycle, then anchor lag signal, then again 8-bit data, then again anchor lag signal, and you have to synchronize it. See, if you are writing a code for 8-bit address, 8-bit data, that code cannot be used for 8-bit address, 64-bit data. Because slave knows that after 8 clock cycle, like according to this project, after a first start state, then his master will send address, then after master will send write data or read data. If you want 64-bit means master should send read data, write data for 8 times. So slave should know that also. So at the start only we fix it. How many times we should loop it. So now here, after that we should, there is a stop state. So here, master sends the stop signal. That means HDL line should go from low to high. Okay. So now, see, in this read acknowledgement state or write acknowledgement state, there is a chance that, okay, if SD is equal to 0, then no issue. See, in this state, before this stop state, there will be either read acknowledgement or there will be either write acknowledgement. So SDA line is always 0. So master should make it from 0 to 1. Or this is one thing, or before the stop state, you can take one stop M state. So here you have to make sure that your SDA line is equal to 0. So when master will make it to 1, stop slave will know that this is my stop. So I should go to stop, then it will go to ideal state. Okay.
Okay. Okay. Yes.
So now here the thing is, you have to know how to convert parallel to serial, how to convert serial to parallel. These two things are important. Okay. Okay, so these are my signals, reset, SCL, SDA. These two are on my
Clock
I2c.
and
Okay.
yes, ma'am.
And
Yes,
these two signals I have taken extra. Okay. To check whatever data or address master is sending, whether I'm getting that or not. See, master will send parallelly. So this is my parallel values. So just to check it. Okay. You can omit it also. That is not an issue. Just to check it, I have taken this one. Okay. So
Okay.
these all are signals why I have taken. You can go, okay, sorry, 1 means write, 0 means read. I have written the opposite, right? So why I have taken this address in means it is a parallel. Like master will send some address signal, slave will convert that serial to parallel. So after converting, it will be stored in address in. When slave will convert serial write data to parallel, it will be saved in this format. Okay. This is the parallel one. Okay. Write read signal to whether it is a write or read operation. This count I have taken to count up to 8 because after 8 clock cycle, I have to stop it and go to egg or next state.
Okay.
So this count enable means always my count should not be enabled. It should enable when I am in address state, data write state or data read state because there I need to count for 8 clock cycle. So suppose so there will be one suppose serial in parallel out, parallel in serial out. So enable means whenever this enable signal 1, then only SIPO or PISO will work. Because all the time I don't need them to work. So it is a good thing. Okay, so if in your SOC any small blocks you are taking, so for each block you should take one enable signal. Because enable signal 0 means that block will not be working and it will consume less power. If you are not taking an enable signal, it will always on working.
Okay. Okay.
Start enable means see, master will send. Okay, so start enable means whenever the start enable signal is equal to 1, at that time slave will wait for start signal. This is, I guess, one optional part. Okay, because slave will always in my project, in this project, slave will always wait for start when idle state. In the idle state only, it will wait for start signal. These are all the states that I have explained. Okay, and this part I will explain later. This is how to design a bidirectional data. This part I will tell later. Okay.
Okay.
See, this address in my address, whatever master is sending.
Yes, ma'am.
Okay, so this is its MSB bit I am assigning to write read signal and LSB bit I am assigning to address out. So it will be the 7-bit output. Here, that 7-bit output. I will check whatever address master sending I am getting here or not. Means from the test bench.
Okay.
So now this is common for all FSM. Okay, so negate of SCL or passage of reset. If reset signal is equal to 1, then present state is ideal, else present state is equal to next stage.
Next stage. Yes.
Okay, so now this is the counter logic. So whenever counter enable is equal to 1, it should start counting. And count enable is equal to 0 means it should stop counting.
No
count
count,
should go to 0. Okay.
Yes.
So now this is slave means see I2c. If I am writing some values with respect to some address and I am reading some values with respect to some address, then there should be some memory to store it. So this is the memory. So whenever write enable, see this write enable, it is my internal signal. my I2C slave will generate this write enable signal. When it will generate the write enable signal? At the 8 clock cycle. When slave will receive all the 8 values, then it will generate one write enable signal. That means I have converted my serial data to parallel data. Now you can store it. Okay.
Okay. Okay, ma'am. Yes, ma'am.
Similarly, read enable signal will be issued to read the values. This is the simple memory. Okay, I can write slave memory like your RAM. Okay.
Yes, ma'am.
Now start condition. So start condition means always at the rate negage of HDA. So if, okay, so start condition, how it is? This is my SCL. My ST should go from high to low. So what can I do? Always at the rate, this is my negage. So always at the rate negage of SDA if SCL equal to high. Because
Then only then it will work.
Because
Yes,
if SCL is equal to low means that can be my normal data transaction. I2C normal data transaction happens in low phase. So in the high phase, if it is having this negage, then it is the start condition.
Sure.
Okay. Similarly, stop condition means
it will be high. SDA will be high.
same. See, passage of SDA, your SCL is high. And here I have taken one stop enable signal. Okay. Stop enable signal means to make sure that it is detecting this in the stop state. Okay.
Okay.
And all other time my stop signal is 0.
Okay.
So now it is the next state. Okay. So from the idle state, see, whenever it will detect the start state, it will make the start signal 1. This start, it is an internal signal. So now my slave will look for the start signal. If slave finds start signal is equal to 1, it will go from idle state to next state. So if start is equal to 1, then it will go to start state, else it will remain in idle state. Okay, so this state, it is optional. You can directly go to state register address also. But why I have taken this? Because it will detect this at the passage of SCL. Okay. So after that, I have taken one clock cycle gap, then I have started. Else after passage of, it will sudden, and let's say what will happen? Here it will detect the start state. Then suddenly here it will start capturing the address. So there may be a chance that master has not sent the data yet. So I just have taken one clock pulse so that master will stable and it will send the next data. So from this page, it will start detecting. I am just cancelling this page. Okay. Because the master is sending start signal means in the next negage only master will send the data. So this negage master is never going to send any data. So I'm just giving one clock pulse delay.
Okay.
So now register address, it will count from 0 to 7. So 0 to 7, okay, sorry, 8 clock pulse here. See, you may think that it is written 6 means it will count from 0 to 6. Okay, so it is a non-blocking assignment. In the counter, I have used non-blocking assignment.
Yes, ma'am.
So non-blocking assignment means if I'm comparing here less than 6, that means it will go from 0 to 7. You can just simply write a counter and check this. Okay, because blocking means it will immediately compare and give the output. But non-blocking, it will compare. Okay, in the next clock cycle, output will be reflected. So that's why it will go from 0 to 7 means 8 clock period. So for 8 clock cycle, it will remain in register address. When counter value is not is equal to 8, it will go to this state. 0 to 7, it will remain here. In the 8th clock cycle, it will go to here. So here it will just remain for one clock cycle. Now here it will check this SDA means it is my SDA signal. So if it is equal to 0 means act. 1 means NAC. So if it is a NAC signal, then directly it is going to stop M. Stop M means this is the stop state. You can go to idle state also.
Okay.
And here what will happen if SD out is equal to 0 means it is the acknowledgement. Next it will check whether write rate signal is equal to 0 or not. If it is 0, okay, just 1 minute, I'm having one call. Okay.
Okay. Okay.
Hello. Yeah. Hi, good morning, Ramana. Fine. Hello. Yeah, just 1 minute. So if this write read signal is equal to 0, then go to write state. If it is 1, then go to read state. So 0 means write, 1 means read. I have written correctly. Okay. Just here I have to change it. 0 means write, 1 means read. Okay.
Yes, ma'am.
Okay. So register address part completed. So here next state write or go to read state. So again in write state similarly count for 8 clock cycle. Okay, you in the 9th clock cycle go to acknowledgement state. In the acknowledgement state, if you are getting 0, then register address. Register address, it's up to you. Register address means I am going to start another transaction. Let you don't want to start any transaction, you can go to idle state. Okay. So here I am doing repeated transaction. My like one address, one data, another address, another data, like this. So this stop aim state means the previous state of stop state. So in the stop aim state, slave will wait for the stop signal from the master. Okay.
Okay, ma'am.
So in the read sem, so all those things are for the 8 clock cycle, it will remain in that state. In the 9th clock cycle, it will go to acknowledgement state. Okay.
Okay,
So now
ma'am.
in the stop aim state, you can see in the stop aim state, it is waiting for stop signal. If stop signal is equal to 1, it will go to stop state. If start signal is equal to 1, it will go to start state. Okay. So here it is waiting for the signals. So next in the stop, if it is going to stop state, so after stop state, it can remain there. Or if it is returning any start signal, it can go to start state also. Okay, so now all the states completed. So now here I have written some output. Output means there is one PISO, SIPO block. Okay, then there is whether data will be from master to slave or slave to master. So all those things will be controlled here. So direction enable is equal to 0 means here I have written it is from master to slave. Where I have written direction enable. See direction enable when it is 0 data from master to slave, when it is 1 data from slave to master. Because there is only one line. So I have to make sure whether it is from slave to master or master to slave. Okay. So 0 means remember master to slave. So in the idle state it is 0. Everything I have kept 0. Only start enable signal is equal to 1. Why start enable signal is equal to 1? Because here slave is waiting for the start signal from master. In the idle state only it will wait. So start enable equal to 1. So in the start state again data will come from master to slave. So direction enable is equal to 0. All the other signals will remain same. Only direction enable must be 0. Okay. So because it is coming data from master to slave. So here also data is coming from master to slave, and here see I have made count enable is equal to 1 because it need to count for 8 clock cycle, and SIPO enable is equal to 1. That means serial to parallel converter. That should be 1. It will convert from serial to parallel. Okay. All the other signals are 0. So now in the egg here data is from slave to master. So slave to master means I have written direction enable is equal to 1. Okay. So now here what I'm doing, so whatever the data I'm getting from serial in parallel out, that value I am keeping in the address in.
Okay.
It is now serially coming, then I am converting it to parallel. Then I am taking one register to store this value.
Okay. Okay.
So now state right, PISO enable 1, count enable 1. Sorry, serial in parallel out enable 1, count enable 1. Then egg state, here direction enable is equal to 1. So now in this state, what I'm doing, whatever the data I'm getting from SIPO, it is converted, it is already converted the serial data to parallel. So now I am storing this data in the write data format. Okay, so in the address, I have stored the address, in the write data, I have stored the write data. So in the next clock cycle, okay, so here my slave enable signal, it is PSO. See, here I have made write enable equal to 1. So now at this state, data will get written to the memory. So I have get my write data and here I have get my address. So with respect to that address, my data will get stored. Okay, so here I have made write enable equal to 1.
Okay, ma'am.
Okay, so similarly state read. So here there will be parallel to serial converter. So whatever the PISO data I am getting, its first bit only I am sending. Okay, so it is like some parallel to serial converter. Data will get shifted to write, shifted to write, and the LSB part I will be giving to master serial. Okay.
Okay, okay.
Okay, so now here just go through once. If at any point you are not able to understand, you can ask me. Now here read enable signal. So if my count equal to 0, then read enable signal is equal to 1. That means I
1.
can read. Okay. Like sorry,
Yes, ma'am.
count is equal to 0 means okay, count will start from 0. Okay, so if it is 0, then read enable is equal to
will be
1.
1.
So read enable is equal to 1 means it is the parallel kind of things. Na? I am reading parallelly.
Yes.
Then I will transmit it to serial. So I just need 1 clock cycle. So when count is equal to 0 means at the initial state, data will got read from the slave. Then my read enable will become 0. Okay.
Okay. Okay.
Okay, so now this part, so here data is from master to slave, so direction enable is equal to 0, here direction enable is equal to 1. This part is important. Okay, so now in the
Okay.
stop M signal only I am making stop enable is equal to 1. That means in this state only slave will wait for the stop signal. If master is sending stop signal, it will go to stop, else it will go to start. So your stop state is basically same as your ideal state, so you can omit that state also.
Okay.
So now
Okay.
here I have written code for SIPO and here PISO. So I have written with respect to this enable signal. Okay. So now next go to here. This line. If someone is asking you how to design one bidirectional port. So in the duty what I have written. So when direction enable is equal to 1, SDA is equal to SDA out. Else it is in high impedance. High impedance means okay, else in high impedance. High impedance means practically it will be on floating state. Okay. So in the test bench, what I should write? See, it is like duty, test bench, or master slave. You can take duty as your slave and test bench as your master. So in the master, opposite things should happen. When direction enable is equal to 0, then data should go out.
Yes, sir. Opposite after this.
So now here what will happen? So when this SDA, direction enable is equal to 0. So 0 means here what will happen? This will be in high impedance state. And it will send a SDA out. So my SDA will be equal to SDA out from here. Okay, let's write SDA out 1. Okay, so it will get the data from the slave. Now when direction enable is equal to 1, it will go to high impedance. Here it will be SDA out. So when it is equal to 1, it should get data from the master. Understood?
Okay, ma'am.
Okay, so high impedance state means whatever the value is coming from opposite side, it will take that. It is like in floating state. Okay. So whatever the things I have written here, it's just opposite thing I have written here. Okay.
Okay.
And
Okay.
this duty dot direction enable means I am directly taking the values from duty direction enable. Because this decides now when it is from master to slave or slave to master. Okay. Then yes.
Ma'am, this duty dot. Okay.
It is
Ma'am,
like
please kindly
hierarchical path.
explain.
Hierarchical
Okay.
path. Duty means, see, here I have given the instance name duty.
Ha.
So go to this I2c slave. Inside this slave, what is the direction enable? Duty dot direction enable. Here let I have given its name
Okay.
as
Okay.
M1. So it will be M1 dot direction enable. So whatever
Okay.
this
ma'am.
name. Okay. So
Okay.
now here I have taken 6-bit address, 8-bit data, 7-bit address, all those things. Okay. So initialization state, I have made all the values to 0. Then reset state to generate the reset. These things are common. Okay. So see, this is the start condition. So in the start condition, what I am doing, I am first making my SD equal to 1. Then I am waiting for passage of clock. Then I am making SD is equal to 0. So whenever there is a passage of clock, at that time SD will go from 1 to 0. So then I have given hash to delay. Hash to delay means this delay. Okay, so it will wait for passage whenever this is a passage, right? So after that, I am giving hash to delay. Here I am making SD to 0.
Okay.
Similarly, stop condition is its opposite. First I am making SD as 0, then I am making SD equal to 1. So now here what I have done, I have taken one parallel values 8-bit. Then I am converting this 8-bit serially. Serially I say in the master side what will happen? It should convert parallel to serial and send data to slave. Right? So now this is how I am converting parallel to serial. Now this part it is not synthesizable. So you can use any logic. You can use piso logic here. So this is the parallel data I am taking. Now I am converting this parallel to serial and I am sending. Similarly in the read, what I am doing, I am converting this is like serial to parallel. Sorry, this is I am giving the address. Okay. This is the write address and this is the read address. Okay, so the address means I am converting parallel to serial. For write data also I have to convert parallel to serial. I am taking one, see here I have taken some fixed data. You can write it to $random also. But if you are writing $random, let you have written into 18 address and you are trying to read from 12 address. Then it will send some X. So what I've done, I have taken some specific addresses. I am writing into 11 address. I should read from 11 address also. So I have taken some specified value so that I can check whether my project is working or not. So this data value you can take random, not a issue, but address should be specific. Okay. So now here I have called all the tasks. Okay, just go through these things. If you are having difficulties to understand, okay. So if you understood the logic, then you can understand this code. Not a issue. Okay. See here address is 5, 5. If I'm taking $random, then it may not be 5, 5 like this. Okay. So next, so here I am getting the data out at CC. So here why HD is equal to X, here you can see this HDA signal. Okay, because I have see data out means slave is sending the parallel data CC. Okay, I have to check it. It should send in this manner only. Why it is sending X? It should not be X here. Okay, but next you can see whatever the value CC I am writing, here I am getting. Like slave is giving the proper data, but it is not converting it to serial properly. So I would modify this code why it is not having serial. But this is only for 2 values I have checked. So you can take $random and check it. Okay. Just try to just once. Okay. If you're facing at any point, ma'am, why this line I'm not getting, I will explain. Okay.
Okay.
And two more things you just go through. Okay. I will provide some I2C interview questions. Okay. First question is, what is the arbitration? Second is clock synchronizing and clock stitching. Now let you have multiple master, one slave. So how you are going to decide that which master should communicate with the slave?
Using select lines.
Here there is no select line. In the FPV we have select line. Here is there any select line? SDA and SCL. So here what will happen? There will be one AND operation. Simple AND gate. And all the SDA line will be connected to the AND gate provided here.
Okay.
All the SCL line also, clock also. So here simple arbitration technique is AND gate.
Okay. Okay.
So how it works? Okay, let your master 1 is sending the values 1, 1, 0, 1. Master 2 is sending the values 1, 1, 1, 0. Okay, now master 3 is sending like let 1, 1, 0, 0. So all they will be start sending at a time. Now there is no select line. Okay. So now AND gate output. So first it will be 1, not a issue. Second it is 1, not a issue. Third value will be 0. So here what will happen? M2 will lose the arbitration. M2 SDL and SCL line will go to high impedance state. Why it is losing the arbitration? Because it is sending 1 and AND gate output is 0. Now 1, 1, 0, it is matching either this value or this value. There is no chance that it can match with this value. So it is gone. So now next what will be output? 0.
0.
So 0 means here M1 will lose the arbitration because M1 is sending 1 but 0 is getting transferred. So what will happen? Okay. So the master who sends 1 first, the master who sends 1 first while other sends 0 will lose the arbitration. Understood? Okay.
Yes, ma'am.
And here clock synchronizing, simple AND gate is used. Clock stitching means, okay. So if slave is sending NAT, so one way is master can drop the transaction. Let master don't want to drop the transaction, master want to wait for slave. Maybe after 2 or 3 clock cycle, slave will be free like this. Master want to wait for slave. So at that time what will happen? The clock stretching, slave will make the SC line low. SC line low means it will be constant only. It will not change. And whenever slave is available, it will make SCL to work normally. Okay, let slave is busy or this kind of thing. So slave is busy means it will make SCL low. So SCL is continuously low means master is not going to send any data. Master will send any data when it will go from low to high, then high to low. But if it is constantly low means master will stop sending the transaction. It is like clock stretching. Clock stretching means what will happen? Clock is working like this. Now let's slave is busy. So what it will do? It will make it like 0. So during this time, master can send only one value. It will send on the neg edge. So this is the neg edge continuously. So whenever it is free, it will again. So this is only simple AND gate with 0. Okay. So here every technique is simple like the AND gate. So you can go through these things. Okay.
Okay, ma'am.
I will send some interview related questions on i2c. Okay. But for first you just go through these things. Okay.
Okay, ma'am.